Is your ground truly solid? Are we building resilient foundations or just hoping liquefaction won't strike? Hi, it's Tariq from MTS Consulting Engineers. Today we'll be discussing liquefaction mitigation strategies, focusing on two main approaches, ground improvement and structural enhancement. As you can see from this image, the impact of liquefaction can be devastating, causing significant ground failure and damage to infrastructure. So what exactly is liquefaction? In simple terms, it's a process where saturated soil loses strength and stiffness. This phenomena is primarily triggered by earthquake shaking. As depicted in the diagram, a stable site with loosely packed grains and water-filled pore space can transform into a liquefied soil when shaking increases the space between grains, causing it to flow like a liquid. The result can be significant ground deformation and severe structural damage to buildings, as shown in the example of a building tilting and sinking. Essentially, liquefaction occurs when you have the right soil conditions, present groundwater, and earthquake shaking. When it comes to mitigating liquefaction, there are two primary approaches. First, we have the ground improvement, which involves modifying the soil itself to reduce its susceptibility to liquefaction. Second, we have a structural enhancement, where the focus is on designing structures to withstand the effect of liquefaction, emphasizing the building's overall resilience. The image illustrates how liquefaction can cause lateral movement, uneven ground, and upward movement that penetrates the surface, leading to damage to structures and foundations. Let's dive into some specific ground improvement methods. The first is densification. The goal here is to increase the soil density. Common techniques include dynamic compaction and vibrocompaction, which effectively reduce the likelihood of liquefaction. Next is solidification, where the aim is to cement the soil. This can be achieved through methods like cement or chemical grouting, leading to increased soil strength and resistance. The image here shows a large area of soil that appears to be undergoing some form of ground preparation or improvement, potentially related to densification and solidification. Moving on, drainage is another crucial method. Its goal is to dissipate excess pore water pressure in the soil. This is done by installing vertical drains or drainage wells, which ultimately reduces the liquefaction potential. Soil replacement is also a very effective method. Here, the goal is to substitute problematic soil entirely. This involves replacing liquefiable soil with less susceptible materials like gravel or by constructing stone columns, directly addressing the issue. The image here shows wet, muddy ground next to a building under construction, which could indicate poor drainage or problematic soil conditions that might necessitate mitigation measures. Another set of techniques falls under reinforcement and containment. The goal here is to control soil movement during an earthquake. Techniques include using geogrid reinforcement or building containment structures to help manage how the soil behaves. Finally, an emerging and promising method is microbial technology. This approach aims to strengthen soil using biological process, specifically by utilizing microorganisms to produce cementation within the soil. The image shows a slope reinforced within a net and cable, which is an example of reinforced and containment to stabilize the ground. Now, let's shift our focus on the structural enhancements method. One key aspect is foundation design. The approach here is to design foundations that can specifically withstand the stress and deformation caused by liquefaction. Examples include using deep piles or specially reinforced foundations. Another method is structural fortification. This involves strengthening the existing structural elements of the buildings, with the goal of allowing the structure to accommodate potential settlement or deformation without catastrophic failure. Continuing with a structural enhancement, avoidance is a proactive strategy. This approach involves careful site selection, meaning choosing construction locations that are not susceptible to liquefaction in the first place. Lastly, we have a structural modification. This approach involves incorporating additional support features into existing or new structure. Examples of such features include anchor piles or retaining walls that provide extra stability. Before implementing any mitigation strategies, economic considerations are crucial. There is a significant cost variability. The cost of ground improvement and structural enhancement can differ widely based on the specific methods used and the unique condition of the sites. Therefore, a thorough feasibility evaluation is crucial to assess the economic viability of different mitigation techniques. The evaluation is essential for making informed decisions and selecting the most optimal solution. In conclusion, effectively mitigating liquefaction requires a comprehensive approach. This typically means combining both ground improvement and structural enhancement strategies. It's important to remember that there are no one-size-fits-all solutions. The best approach always involves tailored solutions that depends on site-specific conditions, the structural requirements of the project, and of course economic factors. Ultimately, ensuring safety is paramount. Investing in appropriate mitigation strategies is vital for protecting both infrastructure and lives, especially in earthquake-prone regions. Now I'm going to end this presentation by saying build right, build safe, and build compliant. See you at my next video. Bye for now.